Okay, so yesterday's class, what did we looked at the telescopic op-amp. So we looked at the all the overall data sheet, right? We looked at the gain, the DC gain, the unity gain frequency, the pole, non-dominant poles, the number of poles at least, and so on. So today we'll do the same thing for the folded cascode op-amp. Okay, but before that there is a couple of things, I think, based on questions which we had yesterday. So right, you had a question on why this would contribute to the pole. Did you try it out? You didn't try working out. Okay, see, what is the use? If I tell you to do something, if you try it out, then that's one thing. Okay, but I mean, I'm not saying this just for you. This is for everybody. I assume the answer was not obvious to everybody, right? So, okay, so now, anyways, let's go through it. What do you think? Why do you think it is going to contribute? I mean, this is to everybody, not just to him, right? First of all, what happens to the current? This is your signal current. Okay, so this is the cascode, right? This is the biasing part of the cascode, the mirror part of the cascode, and this is where you're drawing current. So this is your, I've basically drawn this portion, right? What do you think is going to happen to the IN? Some portion may flow through the capacitor CP, correct? Okay, so what does that do? It flows through CP, that's fine, but that is not necessarily a reason for it to, for the pole to appear at the, so what are you trying to find here first of all? So what happens? So I redraw it slightly. This is the IOT you're interested in, right? Correct? So what are you finally interested in creating? If you want to analyze just the mirror portion, just for this, you need to find out the voltage here, because that is the one which is going to mirror the current. Correct? So if I call this, let us say Vx, you want to find out Vx over In, right? Of S, of course, right? So what happens here? If part of this IN goes through CP, what happens? Of course, that is going to change the voltage Vy here. Let us call that Vy. Vy is now going to be a function of the parasitic capacitance at that node, obviously. Okay. What is the VGS for this transistor? It is actually just Vy. Okay, this node is signal ground. Correct? But there is going to be an output impedance here, and there is going to be a GM. So definitely the current through this transistor is going to be a function of Vy. And finally, overall, what is Vx? GM times Vx is the current flowing through this transistor. So obviously, if this capacitance increases, there is going to be less current flowing through the transistor, right? There is going to be less. The voltage Vx is going to change, definitely. Can everybody see that? Okay. What do you think the pole position is going to be? If you calculate it out, GM by I'll just call it 3, 4, 5, 6. I don't remember the exact numbering. What is it going to be? GM3 or GM5? GM5 by CP. Is that right? So in reality, in this case, you actually have a feedback. Okay? So it's not so obvious. If you have no feedback at all, then what you say may be correct. Okay? You can find out the impedance at that node, find out the capacitance at that node, and calculate the pole position. In this particular case, you have feedback, right, from the gate of this to the input node. So in reality, if you actually calculate the pole position, it won't be the same. It won't be just the conductance at this node over Cp. Okay? Can everybody try it out? It's a, right? This one you just have to write two sets of, just draw the equivalent for this with the output conductance and calculate. This is just Vx. So you are basically calculating the input impedance of this circuit as a function of frequency, correct? So that's one thing. The second thing I wanted to say was, this was with respect to the, let's get the opamp. Maybe this one looks better. We looked at the different poles in each point, right? So I think I called it P1, P2, P3, P4, P5 and P6. I think this is the scheme I used yesterday. And one of the other questions was the relative positions of P1 and P2. And yesterday I actually made a mistake. I should have looked at it more carefully. So if you want to find out P2, for example, it is the conductance at this node. So here there's no feedback. So it is the conductance at this node over the capacitance at that node, right? So if this is Cp2, right? It's approximately GM3. Why? What do you have at the drain side? You have a what is the impedance of this cascode? Input impedance, low frequency, 1 by GM5. Okay, 1 over GM5. Obviously, because you apply a voltage here, it's going to draw current. Just so it is very obvious, it's just 1 over GM5, right? Which is a very low impedance. So in other words, the input impedance looking in here is just going to be 1 over, input conductance is just going to be GM3 and Cp2. Okay, so that side it is correct. But for P1, what I said yesterday was wrong. So obviously, the input impedance here is much larger. So the impedance looking in here is no longer 1 over GM3, right? Oh, sorry, 1 over GM4. What is the expression for input impedance? So if I have something like this, if I have a common gate, plus RD by okay. So in this case, what is it? So I'm going to call this Z1. So sorry, Z1 is 1 by GM4 plus what is RD? What is RD here? It's the impedance looking in there. What is that? Correct? So GM8 RDS8 into RDS6 over GM RDS of 4. Okay, obviously this is going to be of the order of RDS, which is much larger than 1 over GM. So this is going to be of the order of RDS. Yeah, so this is a cascode looking up. What is okay, let me call this Z3. What is Z3? Correct? What is Z1? Plus Z3 over, correct? And that's what I've actually written here. Yeah, so this is Z3 over GM4 RDS4. And this is of the order of RDS. What do you have looking in down here? Another RDS. Correct? So it's going to look something like this, because you have Z1 parallel Z2. Z2 is of the order of RDS. Z1 is also of the order of RDS. Therefore, the total impedance there is RDS over 2. The total conductance is 2 GDS, of the order of 2 GDS. So the pole there is going to look like 2 GDS over CP, whatever passive capacitance is there at that node. Correct? Is that clear to everyone? Whereas P1 is actually of the order of, sorry, P1. Sorry, did I say, I should have said P. Okay? Whereas P2 was the order of GM3 over CP, which is much farther out. Okay, it's almost like, 50 times. Is that clear? Okay. Yeah, just wanted to clarify these 2 points, because yesterday there was, especially the second one, I think I made a mistake. Who asked me? Somebody asked me yesterday about this. I don't remember. Anyway, did you ask me about this yesterday? No. Okay. Okay, so let's look at the folded cascode. So is everything about the telescopic clear? Any questions on the telescopic? Okay. We have looked at this folded cascode idea before. The basic idea is, what do you do in a normal cascode? Let's say you have an NMOS input path. You add an NMOS cascode on top of it, which reuses the same current, and you get a larger output impedance. You can replace this NMOS with a PMOS. Right? So in other words, how do you replace it with a PMOS? You need to be going into the source of a PMOS. Right? In which case, you can't do it this way. You need to fold it down. That's why it's called a folded cascode. So let's say this was your VB, and so let's say this was I1. Okay, so you can replace M2 with a PMOS. Let's say I have I1 here. And right, we have looked at this before. Right, so all you are doing is, the bias current splits like this. The signal current flows out like this from the output. Correct? What is the output impedance of this? It's the same as the other case. In this case, it's GM RDS2 RDS1. Here it's the same thing. There's no difference. Okay? So let's start off building the folded cascode from this basic idea. So we take the same differential pair. So Okay. So you have these two things, and what do? So you want to send the incremental current out, but you want to bias this separately. So let us say we add the current sources I0 over 2 on both sides. Okay. So what is the current flowing? What is the current here? I0 by 2 plus GMVID by 2. On the other side, you have I0 over 2 minus GMVID by 2. So what are the currents flowing here? Oh, sorry. Minus GMVID by 2. Correct? Okay. So now you want to find a way to send this through a PMOS. Okay. Now these two current sources bias the differential path. Now if you are adding some PMOS, they also need to be biased separately. So we'll call that I1. Okay. So let's call this I2. This is pretty much the same as what we did before, right? Is that right? So what happens to this incremental current? You're going to take the output from here, correct? Let me just call it V out minus for now. Okay? You're going to take the output from these two nodes. Very similar to your single-ended folded cascode. Correct? Now, of course, you can combine these into a single transistor. There's no need to have two separate sets of current sources. They're both going from VDD to the same node. But you obviously have to remember the reason it was drawn separately at the beginning is to remember that these transistors, M1 and M2 have bias currents of I0 over 2. So obviously the current source which you have from VDD to this common nodes should be larger than that, right? That is the reason why it was drawn separately right now. But that thing you have to remember, okay? And now, how do you build these current sources? Yeah, using a transistor, you use a current mirror, right? So now, these two guys put together can be replaced by a PMOS. Okay. What do you do for these guys? For I2, you can do the same thing, right? They also have to be current mirrors. What would you use here for I2? NMOS current mirror. Okay. Would you use a normal current mirror? So let's say you use a normal current mirror. What is the output impedance looking down? GDS. What is the output impedance looking up? GDS. Is it just GDS? GM RDS times RDS, right? So it's much larger. So it doesn't make sense to just add a single NMOS. You add a cascode at the bottom side also. In other words, if you're going to replace these with transistors, this guy acts as a cascode for these guys also. So your output impedance is much larger. if you want to have a good DC gain, you want to convert the bottom side also to a cascode, right? So now we can redraw it slightly better. Okay. Is that clear? All I've done is I've replaced the current sources with transistors. On the top side, you replace them with a single set because you already have a cascode. On the bottom side, you replace it with a high swing cascode, just as we had for a telescopic. Okay? So let me number these transistors, M3, M4, oh sorry, and M10. Okay? So let's say this side has VD over 2, this side has minus VD over 2. Okay, so this side has I0 by 2 plus GMVD over 2. Okay. What does this side have? Let us say this has I0 by 2 plus I1. This one has I1 minus GMVD over 2. Correct? So you're drawing current from here. So the current going down is minus GMVD over 2. Okay. So if I have some load here, for now I'll assume it's a capacitance. What is the total current flowing out? What is it? Right, I should have said it's GM1. So the current flowing out is GM1 times VD. Okay. So this is the same as your single stage or telescopic, right? There's no difference. So your large signal transconductance is GM1. What is R out? So let me say right, you have two components, looking up and looking down. What is R out P? GM6 R6 RDS 10. Is that all? In parallel with RDS of 2, correct? Okay, that is R out P. What is the bottom side? It's just GM8, RDS8, RDS4. Is that clear? So this is your DC gain. Did everyone get that, or do you want me to repeat it? Everyone got it. It's pretty straightforward. Yes. Sorry. Yeah. Okay. So the impedance looking in here is RDS2 parallel with RDS10. Correct? The impedance looking in here then is GM6 RDS6, GM6 RDS6 times RDS10 parallel RDS2. That is the impedance looking up. The impedance looking down is just GM8 RDS8 times RDS4. Right? So the overall impedance is just a parallel combination of those two, and the overall gain is just GM times R out. So GM times this guy. Okay. So if you compare this with the telescopic, what do you think is? How does this compare to the telescopic? Smaller. Not half, because on one side it's half, on the other side it's not. So it's probably going to be more like 2/3, right? So DC gain is okay. DC gain is slightly smaller than the cascode gain. Okay. What else? Let's look at. So this is the first one, right? DC gain. What is the unity gain frequency? GM1 by C, same as before. What about the non-dominant poles? How many, what all nodes do you have poles at? So let me start naming these. I think I have a convention. So similar to what we did for the other one. Okay. P1, P2. P5, P6, right? You actually, turns out you actually have the same number of nodes as before. We had 6 nodes in the telescopic, we have 6 nodes here, right? And it turns out that the dominant pole is still good, right? It's still your dominated by your output, okay? And again, you can go about calculating the dominant poles, and you can try to find out what do the impedances look like. You can see this pole, for example, looks similar to what you had in the other case. There's not a big difference. This pole also looks the same as you had for the telescopic. Now one difference is that P1 and P2, they're actually slightly, because now you have 2 RDSs in parallel, they look slightly different from what you had before. Okay. Now the other thing is, What do you think will be the relative sizes of M9 and M10 in this case? They should be larger because now they're carrying I naught by 2 plus I1, right? So you would expect them to be larger, correct? Because they're carrying a larger bias current. In which case the parasitic capacitance at nodes P1 and P2 are also larger. So you would expect the non-dominant poles to be a little bit closer in compared to your telescopic. Okay? So you would expect these. You added one more? Yes. So? Correct. So you can't tell, but to a large extent, conductance has actually come down by half. Now, conductance is actually doubled. The capacitance, on the other hand, you don't know yet what I1 is going to be. Okay, whether it's larger than, if it is, let's say, equal to I naught over 2, you can say maybe you have just doubled the transistor. If it is larger, it's difficult to say. Okay. So, okay, definitely we can say this. What is the next one? Noise. What is the noise of this going to look like? What sources of noise do you have here? What sources do not contribute any noise? M7, M8, M5, M6. Right? They are cascode devices, so they will not contribute noise. Is that right? Is that right? So to first, you can actually neglect the noise from these guys. Okay? Yes. Why it does not contribute noise? Okay, we studied this almost a month back, right? Okay. So, okay, I can go through this again. So if you look at the noise of the cascode as an input referred signal, what is the impedance looking down here? RDS. So what is the gain to the, so output is shorted. What is the noise flowing through the output? So if I have a VN here, what is the noise flowing through the output? What is this? What is it? So you want to find out the effective transconductance of this. What is the effective transconductance of this? Right? This is obviously very large. Right? So now you see why the noise is very small. So this is approximately equal to Vn over RDS1. Which is very, very small if RDS is large enough. Okay? But yeah, the things which we spent a long time on, like the first few classes, things like the cascode noise, output impedances, input impedances, the reason why we spent a long time is so that you will internalize them and then remember them, and we'll use them, quickly when we go through the bigger circuits, right? Okay. So these four devices will not contribute noise. What about the other? What other devices contribute noise? What happens to noise from M1 and M2? they appear directly at the output, right? It's just like a signal, right? You have a, just like you have GM by 2 going to the output, you'll also have the noise of M1 and M2 going to the output. There's not a lot of difference. What else? What about noise from M3 and M4? They'll directly appear at the output. What about M9 and M10? They'll also appear at the output, right? Okay, so you have 6 noise sources. So the output noise density is going to look something like this. What was it for the telescopic? One and 3, GM1, we didn't have the GM9 term, right? So noise of the folded cascode is definitely larger, correct? What can you say about GM9? It's probably quite large because remember M9 and M10 are larger devices, they carry larger current. So quite possibly GM9 and GM10 are going to be larger, I mean significant, not larger but significant. So the noise is going to be significantly more, okay? Okay. So if you look at the input referred noise, this is what we did earlier, so nothing new about it. What do we have next? Offset. So the offset of VT offset of 1 and 2 appears directly. Very similar to what we had before, right? Except you have one more term. Right? The expression was very similar to what we had for noise, and we have an extra term here, which is from your 9 and devices 9 and 10. Okay? Sorry, GM9 by GM1. Okay? GM9 by GM1. So it looks like so far, things have been bad. DC gain has been, lower. Non-dominant poles have moved definitely. Possibly they have moved in. Noise is larger. Offset is larger. So what do you think is the advantage of this op-amp? Right? The output swing. Correct? Because in the earlier case, we did have a strong limitation. What was the limitation on output swing of the cascode? Either the single stage or the cascode, we had a fundamental limitation because the output cannot swing VT below VBN, correct? And VBN needs to be biased larger because you want to give enough headroom for M1 and M2 to be well into saturation so that the distortion is lowest, correct? So which means your output swing is heavily limited. In this case, you have actually broken that by actually breaking the output bias completely from input bias, you have broken that connection between input common mode and or the headroom for M1 and M2 and the output swing. So now your output can swing as high as VDSAT 9, VDSAT 5, right? 9 and VDSAT 5. Okay, they're all identical. I'm just don't worry about it. If I say 9 or 10, it's the same. 5 or 6 is the same. Okay. Yeah, so it's VDSAT 7-8 plus VDSAT 3-4. Correct? These devices plus these devices.